So the key messages of this segment of the lectures are that realistic doping profiles form a triangular quantum well in the emitter. These are confined states in the emitter that, if left alone, have very long lifetimes or very narrow states in a mathematically ideal case. We can compute them, that's fine, and I've showed you IVs that have that, but it's physically unrealistic. It's physically unrealistic because you have a high electron density in the emitter under equilibrium conditions. So you have effectively very strong scattering. So it's strong equilibrated scattering, and the states are broadened. So in NEMO, we introduced an empirical broadening model, and that is based on partitioning of the device into reservoirs and a negative region. The reservoirs are non-Hermitians, and we compute charge only, and the central negative region sees the effects of these thermalized states in the emitter and the collector. And for typical high-performance indium gallium arsenide, indium aluminum RTDs, we set that relaxation to eta to 6.6 milli-electron volts, and which corresponds to a scattering time of 0.1 picosecond. And my point of caution here is that this is an empirical fitting parameter, and you shouldn't use it to match experimental data. So what we have done throughout the NEMO simulations, we set it to 6.6 milli-electron volts and don't change anything, because you can ramp the current up and down with this eta. So if you have very much stronger scattering or eta in the emitter, you will ramp up the current because the resonance gets broader. So that's an empirical fitting parameter that you should really do honest physics about, and we can continue to work on improving that scattering model. So, do you have any questions? Yeah?
Just to understand if I put the question, I say if we should consider the device region, in the device region also the bonded state before the barriers, and so calculating this self-energy outside this region.
Yeah.
We should avoid putting this relaxation time, as we are considering just the relaxation in the outer product, let's say.
No, what you, oops. So what you do is, so the question is, effectively, where do you apply your boundary conditions?
Yeah.
Right. So what we do is, so here's the central device, and it's sort of zoomed in. We actually march numerically all the way to that flat band boundary condition. And we calculate a boundary self-energy all the way back from here, and we march it in numerically to this point. And do the same from the collector. And I will actually have a lecture segment on how that is done. So you apply true open boundary conditions at the very far end. So there's outgoing waves and incoming waves. So there's no artificial reflections. And then you numerically walk them into the central device region. And as you've walked them in, all the potential variations and the relaxation is being recognized as such. And you have a numerical boundary condition that has all these effects built in. And there, again, there's a lecture segment. I'll walk you through that. First, I want you to understand the concepts, not the math.
Usually, the very interesting part is somehow putting a physical eta parameter, because
right.
Usually what I was seeing up to now is just eta for making self-energy convergence, so no physical meaning behind the...
Well, the physical meaning that I attached...
Now, if we put such a parameter, I suppose that we put it in the Hamiltonian, as you said, and then we calculate the green function with this eta. While usually you see eta just like make it converge parameter with as small as you want.
Oh, yeah.
And with perfect normalization.
Yeah.
But it's not the case.
No, here it has a physical meaning. Rather than, I know what you mean. You say, to distinguish between the advanced and the retarded green function, introduce a small eta that allows you to distinguish between. No, this now has a physical meaning. That's right.